Last time we talked about water cohesion and adhesion, we were talking more about individual molecules. Today we're going to talk about how water molecules act and molecules in general, how they act on a bigger scale. And to talk about this, we need to understand the motion of molecules. And the fact is that all molecules are in motion. And in terms of this motion, we can say the molecules are moving a little bit in terms of low motion, or they're moving a lot in terms of high motion. And so what the molecules are doing, how much they're moving, is greatly dependent on temperature. And so the greater the temperature, the more movement we have. Let's say movement of molecules. And so at low temperatures, we have ice, which is a solid, and the water molecules, while still moving, they're not moving nearly as much, and so they take on the properties of being a solid. Once we reach the melting point, as the temperature continues to rise, we have liquid water, what we refer to often as water. They are moving around to the point where water takes the shape of its container, right? We pour water into a jar, it takes on the shape of that jar. And as we continue to move up the temperature range with water, eventually we reach the boiling point at which water becomes water vapor. And at this point, the molecules are moving very rapidly. And as these molecules are moving, whether we're talking about solid, liquid, or gas, as these water molecules are moving, they're bumping into each other and bumping into other things. And so in the case of liquid water, even if we had a glass of water and we let it sit to where it was very still, although we cannot discern that they're moving with our naked eye, these water molecules are constantly moving around in here. And they're bumping into each other, they're bumping off the sides of the container, and they're bumping into whatever might be dissolved in the water as well. In the vapor phase, the water molecules are moving with much, much more velocity. Okay, they're moving much more fast. And so when they bounce into each other, they bounce into each other with greater force, and they bounce off of each other with greater force. And so they tend to be much more spread out. And this is why, no matter where you're at, there is some water vapor in the room with you, and you can swing your hand back and forth. You can feel the air. In other words, you can tell that there's something there, but there's enough space in between all the particles, the water molecules and the oxygen and the carbon dioxide and the nitrogen gas that makes up our atmosphere. You might be able to feel some of those molecules, but it doesn't really hinder your movement very much. Now, take the example of if you were in a swimming pool or in a bathtub and you're moving your hand back and forth in the liquid, while your hand could move relatively freely through the liquid. Because the molecules are much closer together, it's harder to move your hand than through, the so-called thin air. Now, if we have a source of water molecules, let's just say it's a source where these water molecules come from. In the source, or near the source, we're going to have a relatively high population or concentration, we could say, of water molecules, because that's where they're coming from. Let's say we turned on a faucet. Okay? And so we could say that in terms of water concentration, it's fairly high. Now, in this course and in chemistry courses, we often use square brackets like this to talk about the concentration of something. And so in this case, I'm going to say H2O concentration, and it close to the source, I'll write high as a subscript outside of these square brackets. And for the rest of the semester, anytime I write these square brackets, we're talking a concentration here. So the concentration near the source is high. Now, far away from the source, the concentration of water is lower. Okay? And so initially, there's a region of high concentration of water, and there's a region of low concentration of water. And when you have two regions where one is high and the other one is, relatively speaking, at least lower, this is what we refer to as a gradient. So anytime we have, it could be water, it could be a salt, it could be anything, a high concentration in one area and a lower concentration in another, we refer to this as a gradient. And so in this case, we would say this is a water molecule gradient. Now, water molecules, and just any kind of molecule or atom or ion for that matter, behave in certain ways. Now, keep in mind all these molecules are moving around, and as they move around, they bump into each other, and they bump into each other randomly. And when two things crash into each other, they tend to move in a different direction. And so as they continue to bump into each other, some of these water molecules get bumped away from the original source. Okay? And they'll keep bumping into each other, and molecules, let's say, that are sharing this space as well. But the general phenomenon here is that water molecules, and any kind of molecules, are going to move from a region of high concentration, because they keep crashing into each other, into a region of lower concentration. And this movement is what we refer to as diffusion. Okay. Diffusion is the movement of molecules or ions from a region of high concentration to a region of low concentration. When we have molecules in greater concentration in one area than another, we call it a gradient. So when molecules move like we have them depicted here from a region of high concentration, let's say higher, and they move to a lower concentration, we say that this movement is along the gradient. Now they'll do this all by themselves. We don't have to add any sort of force or help them along in any way, shape, or form. And so moving from high to low is called along the gradient. If we have a situation where the molecules happen to be moving from a lower concentration area to a higher concentration area, this is said to be moving against the gradient. Okay. Now, this is what naturally and normally happens. This does not usually happen, okay, or it doesn't happen all by itself. So for this to happen, this is going to require work, or is going to require, let's say, some energy if a cell, let's say, wants this to happen with water or with some other kind of molecule. And we'll get into some examples of that later in the course. Now, with plain old diffusion, eventually these water molecules continue to move, and as they continue to move towards the area of lower concentration, the concentration of the water gets higher relative to the original source. And if the source is shut off at some point to where we don't have any further influx of water into the system, eventually they will diffuse on their own until the concentration is equal in both locations. And if we have this situation where concentration in two regions is equal, should be square, we will still have movement of molecules, and so I'll use a double-ended arrow there to signify they're moving in both directions, but we say that this is at equilibrium, meaning there is no gradient anymore thanks to diffusion. Now, once again, water molecules are not the only thing that diffuse and are not the only thing that exist potentially in gradients. Things that are dissolved in water will do the same thing. And so let's take an example of, let's say you wanted to make some tea, okay, or a Kool-Aid or whatever you want to make. Let's say a sweetened drink, which is mostly water. You start off with just plain old water. And if it's just plain water in this container, the water molecules are moving around, but they take the shape of the container, and as long as they're in this liquid form, or the liquid phase, they're pretty much going to stay in here. We'll have some evaporating from the surface, and we'll get into more of that later. But for now, let's just keep talking about plain old diffusion here. If we were to take, say, some sugar and add it to our pitcher of tea or Kool-Aid, if we use very large particles of sugar, they're going to immediately sink to the bottom, right? But if we use, let's say, some powdered sugar, they will probably dissolve readily when they hit the surface of the pitcher. And so when they dissolve, they're floating around in and amongst the water molecules. And since these water molecules are moving around, they are bumping into not only each other, but they start to bump into these sugar molecules. And so in terms of the sugar, initially we've got a region of high concentration. And let's say down here in this corner of the beaker, we've got a relatively low concentration, let's say in terms of sugar. All right. And so how do you think they're going to move? Well, they're going to move in two directions. They're going to diffuse towards these regions where they have a low concentration. And after time, or over time, we will have, you end up with a pitcher or a beaker. Let me get my colors straight here, where we have equilibrium in terms of the sugar molecules. In other words, we could take a sample from anywhere inside of this pitcher, and we should find the same concentration of sugar molecules. Okay. Now, at the same time, when we add sugar up here, we're affecting the water gradient. And when we add the sugar here, now this is no longer pure water as opposed to the water down in here. And so in terms of water, we have an area that's relatively high. Let's say H2O. And up here, we have a much H2O that's much lower. And so the water is going to want to move from high to low, and it will. And so we'll have diffusion going on of the sugar and of the water molecules simultaneously until we get everything well mixed up to where we have equilibrium with both the sugar and the water. Now, keep in mind that these molecules moving around, the more they move around, the faster all of this stuff happens, because this is all due to these molecules bouncing into one another. And so how can we speed it up? Well, how do you speed up dissolving sugar into your Kool-Aid? You can introduce more movement by sticking a spoon in it and stirring it up. Or if you're saying, let's say, making iced tea, you probably have noticed before that the sugar is much more rapidly dissolved when the tea is hot than if the tea has already been iced. And that is true to holding with our discussion of the movement of molecules, and that the hotter or the warmer the temperature, the more they're moving around. And so, in either case, you could speed up this process by stirring or by adding heat. Now, the process of diffusion is relatively slow, and the rate at which it occurs is based on temperature, but also on the size of molecules. So sugar molecules have a formula of C6H12O6, which is a relatively large molecule. It's got, let's see, 12, 6, and 6. It's got 24 atoms in one molecule of sugar. On the other hand, if we took table salt, sodium chloride, and put it into solution, it splits up into sodium ions and chloride ions, which are basically like single atoms. And so they would diffuse more rapidly than the sugar. But in either case, unless we stir it up or add some heat, diffusion is a pretty slow process.